So this week we're going to be talking about the Fischer esterification reaction, and our target molecule this week is going to be making methyl benzoate. Just a couple of things about methyl benzoate to start with. This is the scent of the snapdragon flower. So if you've ever smelled a snapdragon flower, that scent that you smell is actually largely due to this simple organic molecule known as methyl benzoate. It's believed that the flower actually generates this as a bee attractant for pollination purposes. And this can be made in the laboratory using what's known as the Fischer esterification reaction from several inexpensive and readily available starting materials. We're going to start off with benzoic acid, which is fairly inexpensive and readily available. We're going to use some sulfuric acid as a catalyst. We don't need a whole lot of it. And we're going to use methanol, and we're actually going to use a large excess of methanol in this particular case. Notice this is an equilibrium reaction, and we will get the methyl benzoate. Now I should point out that the snapdragon flower does not actually synthesize methyl benzoate this way, because obviously sulfuric acid is not something that a living organism would want to have in this case, like a flower, and so it would be quite toxic to it. However, there is another mechanism that's given in your lab manual where the snapdragon flower uses a molecule known as SAM, or S-adenosylmethionine, to actually make methyl benzoate. And you may be asking, why are we not using that particular route since it's more biologically relevant? And the reason is that on a per mole basis, SAM costs over $290,000. So your lab fee dollars just aren't going to go far enough to do that. However, we can use methanol, which is significantly cheaper. It's available to us at around 50 cents per mole. So we're going to use the Fischer esterification route to do this. And this is actually a very important process, both industrially as well as in academic laboratories. So starting off with benzoic acid, we're going to dissolve that in methanol and add a catalytic amount of sulfuric acid, of course a strong acid. And so what happens in the first step, and all of these steps are reversible, is we can of course think of sulfuric acid as simply as H plus HSO4 minus in solution. We know it completely dissociates in solution. And so what happens is the carbonyl oxygen will react with the H plus to become protonated. This is actually the Lewis base oxygen. And so we end up with the protonated benzoic acid. That puts a formal positive charge on that carbonyl oxygen. Not only does it put a positive charge on that carbonyl oxygen, but it also weakens this pi bond significantly so that weak nucleophiles can attack it. And it turns out that we've got methanol around, which is a fairly weak nucleophile. And so now the methanol can come in and attack the carbon. The oxygen of the methanol can attack the carbon and break that weakened pi bond in such a manner that we generate our new carbon-oxygen bond that we need. And now we have a protonated ether, if you will. Now we undergo a proton transfer, where the proton goes from this oxygen to one of these. These are actually equivalent. I'm going to show it going up to this one. And I represent proton transfers by using a squiggly line and an H+. So I'm showing that the oxygen here is becoming protonated. And of course, this now looks like water, which is a good leaving group. We've just generated the water. Now we've got the protonated methyl benzoate, and all we have to do now is just deprotonate that. Water can do that quite well. We end up with our product. plus H3O. And we have to get our H3O back because I told you that we're using sulfuric acid in catalytic amounts. So we started with H+, we get H+, that's why we don't have to use a whole bunch of sulfuric acid. We're actually using a very small quantity of sulfuric acid relative to everything else. So now, interestingly enough, you're going to be able to push this reaction to completion. So this reverse arrow that I originally drew here is actually going to be quite small. And all of these steps are equilibria processes. So how is it that we're going from the acid to the methyl benzoate? It turns out that we're doing this by using a huge excess of methanol. So by using a large excess of methanol, that's on this side of the reaction arrow, we're pushing that to completion. There's a couple of things else that we could have done. We could have removed the water from the reaction. We could have dehydrated it. Or we could have used a huge excess of benzoic acid. That becomes a little more expensive. Or we could have tried to distill out the methyl benzoate as the reaction proceeded. However, that's kind of complicated by the fact that it's also got this fairly volatile methanol in there. So what we've decided to do is just use a huge excess of methanol, which you will then extract out the excess at the end. So that's going to push the reaction using Le Chatelier's principle all the way to the right by using a large excess of methanol. Now I want you to go through the procedure and actually calculate the excess of methanol relative to the benzoic acid before coming to lab. So you need to know, to an approximate level, how many, what's the excess of moles of methanol relative to benzoic acid. Just another point, it's very important that you get this dried and actually get it isolated before the end of the lab, because you're going to be using this product in the next laboratory as your starting material in the Grignard reaction. So it's very important that you get this isolated, get a good weight on it, and make sure it's dry and stays dry for next lab period when you'll come in and actually use it in the Grignard reaction.